All right, so this is the notes for Chapter 8, Section 2, Part 2, Day 2, however you want to look at that. Still talking about vectors in the coordinate plane. And if you do want to reference the textbook paper in the actual physical book in the class or the online textbook that you can see anywhere, then look at textbook pages 494 through 496. So if something's not clear and you just want to see some more pictures or explanation or whatever, that's where you would find this information. That's where these examples come from and all of that. All right, so now we're going to talk about a linear combination. So you take a vector and write it as a linear combination. This is really the notation mainly used in physics. So vector v in its component notation with the vector parentheses looks like this. And we could write that as a linear combination with the I and the j, where the positive x-axis, the unit vector in the direction of the positive x-axis is denoted as I vector 1 comma 0, and the y-axis with j. All right, so one big thing that I know can be confusing because we keep going back and forth, but this, we're going back to when we were on the trig on the unit circle and all of our angles were measured counterclockwise from the positive x-axis. So anytime we're just doing more math focused, not talking about directional, we're not talking about north, south, east, west, so nothing to do with the map, we're going to rotate counterclockwise. Whenever we have a problem that discusses the cardinal directions, north, south, east, west, then your 0 degrees will be at north and you will rotate clockwise. I know this can be confusing, but that's just the way math is. So we're going to be rotating counterclockwise when we're talking about vectors in the linear combination sense. All right, so write as a linear combination. So here we have let vector DE be a vector with initial point D and terminal point E, written as vector DE, as a linear combination of the standard vectors I and J. All right, so looking at this, first we have to take our initial and terminal point and we need to write them in component form. So first we're going to switch to component form. Component form. So we're going to write vector DE equals, and we're going to component form, and we're going to take the x values, or the final minus initial. So the final one is 4 minus the initial, which is negative 2. And that gives us the A of the vector, this A. And then we're going to take the y values, the 5 of the final y value, and we're going to subtract the initial y value, 3. Subtract 3. And that gives us the component form of the vector. So 6, 2. Okay, so now that we have it in component form, we can write the linear combination. So we're going to take component form, 6, 2, and we're going to take the A, because remember component form, this is A, B, and the A of component form gets the I, because it's, again, similar to, I know all these letters. I'm trying to keep this as simple without mixing as many letters as I can, but the positive x-axis is associated with the I vector, so 6, so I'm going to write this vector 6, I. You can just do a regular I or this little, I believe they call that a hat in physics. I'm not 100% on that. I hat plus 2j, because that's the b with its little hat. So that's the linear combination of the vector, 6i plus 2j. Okay? Linear has the letters in it. All right, so then the next topic is component form given direction and magnitude. So we already talked about component form, and like this one is in component form. But now this is component form given direction and magnitude. And it tells us that component form is obtained when a vector is broken down into its individual x and y components. Okay. And we have a formula here. So I'm going to write my formula. Vector v equals our component parentheses absolute value or magnitude of vector v cosine theta, because we're talking about a magnitude and a direction. Direction is angle, comma, so again cosine is in that x position, just like when we were talking about trig identities. Cosine was always associated with x. Sine was always associated with y. So the y piece is going to be the magnitude of v sine angle theta. All right, so we're going to find the component form from the vector v with magnitude 10. That looks important. We have a magnitude of 10 and a direction angle 120 degrees. All right, so we're going to use this formula to write the component form given direction and magnitude. The vector v equals, I'm going to use this, so the magnitude, the symbol denotes magnitude. I have the magnitude, it's 10, so I'm going to put in 10. And then cosine of angle theta, I have an angle value, it's 120 degrees. Comma. And then the magnitude times sine of theta. So the magnitude is 10 times sine of the same angle theta. And there we have it. Now we can just, all we have to do is simplify and get this as simple looking as we possibly can. Okay, so vector v equals 10 times, so 10, cosine of 120 degrees. So you need to know what the cosine of 120 degrees is. And I just had a unit circle, but I don't know where I put it, so I was going to point it out for you, but you can reference a unit circle, or if you still have them memorized from when I was having you memorize your trig values, that works too. But the cosine of 120 degrees from the unit circle is negative 1/2 for the cosine, comma, 10 times the sine of 120 degrees, again, reference the unit circle, sine of 120 degrees is square root 3 over 2. Okay, so we simplified it down, we got rid of the trig functions, we just have values there. And now we can simplify this because we have 10 times negative half. Well, negative times a positive is negative, so I have negative half of 10. Half of 10 is 5. So v vector equals negative 5. And stuff like that you really don't need a calculator for. You should really try practicing doing simple things like this without a calculator. Positive, negative makes it negative. I have half of 10, that's 5. No calculator needed. 10 times square root 3 over 2. All right, this one may seem a little more complicated at first. Square root 3, I don't know. I'm not going to make that a decimal because that wouldn't be very useful. It would not be exact. I'm going to leave that alone. I have a 10 times a 2 in the denominator, so that's 10 divided by 2. again, 5. And I have a square root 3, and since it's in the numerator, it's times. So that's just 5 square root 3. Done. So there is the component form given the magnitude and direction angle. Let's try one more. Feel free to pause it. Try it on your own. All right, this time we have the magnitude given without words, just given this way. The magnitude of vector v is 24. And this time our angle theta, which is our direction angle, is 210 degrees. So I'm still following the same formula here. There we go. So vector v equals magnitude of vector v, which is 24, cosine of the angle theta, and I know the angle is 210 degrees, and then I have magnitude, again, 24, times the sine of the same angle theta, 210 degrees, and then simplify. Vector v equals, I'm going to save the 24 for later, cosine of 210 degrees. Again, if you know your unit circle, then you know that's negative square root 3 over 2. If not, then I will allow you to use a unit circle for reference on a formula sheet. That's fine. So parentheses, negative square root 3 over 2, comma, bring down the 24. Sine of 210 degrees is going to be negative 1/2. All right, so now we're just going to simplify this one more time. Vector v equals the components. 24 divided by 2, that's 12, and it's negative. So negative 12, and there's a square root 3 there, negative 12 square root 3. Parentheses, again, 24 divided by 2 gives me 12, and here I have times negative 1, so negative 12. And there it is. Not too bad. All right, just a little bit more on the back of the page. Direction angle of vectors. Direction angle of vectors. Angle as measured, again, we're talking about counterclockwise. Since we're not talking about on a map, the only time we're doing clockwise from a 0 degrees at north is when we're talking about north, south, east, west. Normally it's talking about a map, your cardinal directions. But this, we're not. This is just math quadrants. Positive x-axis is 0. Counterclockwise means we go up from 0. All right, our formula, tangent theta equals the magnitude of vector v sine theta over the magnitude of vector v cosine theta. Oh, look at that. Tangent equals sine over cosine, because magnitude over itself, that would be 1, right? So we could also summarize this as, remember with the A, B notation, when I said the vector component form is A comma B, similar to an X and a Y, right? And sine always went with Y, so sine is going with B in this notation. So this could be, and if the magnitudes cancel each other out, because anything divided by itself is 1, then we have B over A. There we have it. All right, so now find the direction angle of vectors. Find the direction angle of each vector to the nearest degree. I have vector P, and it's given to me as a linear combination, 3i plus 7j. Well, first I want to take that and I want to write it in component form. So I have Vector P equals 3, because my A comes from whatever is with I, and my B comes whatever is with J. And I need to look at this, because if this is minus, then that means I have a negative. But it's positive, so this is a positive 7. So 3, 7, to switch it to component form of the vector. So the direction angle, tangent theta, is equal to, so I wrote this out, but then I'm just, because tangent is sine over cosine. But my conclusion was here, so really I just need this part. Tangent theta is equal to b over a. This was just me showing you how I got to b over a. So b over a. I know what b is, because remember I just did that right here. This is my b value. This is my a value. So tangent theta is equal to 7 over 3. But I want the angle. The angle, theta, would be equal to the inverse tangent, tangent to -1, of the ratio of the sides of the triangle, 7 over 3. And make sure you're in degree mode, and you can calculate it. Second tangent, 7 over 3, and you get 66.8, which we're going to round to a whole number. So round to the nearest degree, so it's about 67 degrees, because that 8 tells the 6 to go up. 67 degrees. So also real quick, before we move on, I'm going to show you on our quadrant. Again, if this was x's and y's, if we had tangent is 7 over 3, that means positive 7 is going up and 3 is going over. So it would be going over 3 here on the x-axis and going up 7, like that. And the theta is where it always is, right there. And there we have it. One more example to try. Vector R. Again, first I want to write this in component, oh, it is in component form. This is my A, this is my B. A is 4, B is -5. So I want the angle for this vector. So tangent theta equals B over A. B is -5, A is 4. And then find the angle, theta, equals the inverse tangent of -5 over 4. So it tells me it's negative 51.34 degrees. So we're going to round that to the nearest degree. 3 tells the 1 to stay the same. So negative 51 degrees. That's my answer. That might seem strange. So just to be sure, I'm just going to sketch it and see if this makes sense. So here we go, sketching it. My B value, so my rise over my run, or sine over cosine, however you want to think about it, is -5, or my B, or my A, or my X, again, however you want to think about that, is right here, and that's 4. 4 to the right, positive x-axis. And then I'm going down, because it is down, because it's -5. And then connect to x. So again, it puts theta right here. And for me to have an angle from positive x going down from positive x, that's a negative rotation. So I should have a negative angle. Or we could think of it as in quadrant 4, if we think of all students take classes. Remember, that tells you what is positive in that quadrant. Well, tangent is negative, because we have tangent is negative in quadrant 4, so we have a negative tangent and it's a negative angle. All this stuff kind of comes together, and there you have it.